So, hello everyone, welcome to another video. So, imagine I gave you a box containing thousands of vectors, right? So, do you actually need all of them? Or could a small set of vectors recreate everything that you want? And that question leads to one of the most beautiful ideas in linear algebra, which is the concept of basis and rank. So, before that, let's recap what all we have done up till now. So, we started with vectors. Then we studied about matrix. After that, we studied about vector spaces. And then we studied linear independence. So in the last video, we learned how to identify redundant information through the concept of linear dependence and independence. But what if we remove all redundancy? What if we are left with no redundant information, right? So with that, let's come up with something called as span. So suppose we have a vector space V, okay, and as you know, we define vector space with two operations. One is the inner product and one is the outer product. Inner product is for addition and outer product is for scaling, right? So we have in this vector space V, we have a set of vectors which we'll call A. Suppose x1 up till xk, right? And this is a subset of suppose V. Now, if every vector, suppose V, which belongs to V, we can express them as a linear combination of this x1 to xk, then A is called the generating set of V. Generating set of V. So basically, a generating set, what is a generating set? It is a set of vectors whose span equals to the whole vector space. So what is span exactly? So span is a set of vectors in the set of all possible vectors you can get by taking linear combination of those vectors, right? So suppose I have this set A, and if I take all possible vectors in A and do the linear combination, so whatever the resultant will be, all those resultant will be span, right? Suppose for example, to give you an example, suppose v1 equals to 1 0 and v2 equals to 0 1, then the span of v1 and v2 will be written as a and 0 plus b 0 1, where a and b belongs to r. So this gives every vector a b in the plane so that their span is the entire 2D plane. So like in short, span is all vectors that can be formed using the given vectors. So like in this, the given vectors were x1 to xk. So everything that we can form from these vectors will be the span of A, in the span of A. Now, what is a generating set? Generating set is a set of vectors whose span equals to the whole vector space. Like every vector in the space can be written as a linear combination of those vectors. So span is just basically a collection of all vectors you can generate from the given set of vectors, and generating set is a set of vectors that generates a particular space, right? So in this, the span of A will be everything that we get by the linear combination of these vectors, and A itself, it's called the generating set because we are using the vectors present in A to generate the span. So suppose if S, I'll write again as like 1 0 and 0 1. So in this, S is the generating set for our two-dimensional space, whereas span of S is this. I mean, we can get any vector in the two dimension using this. So the span becomes r square, and not r square, I mean the two-dimensional space, and S is the generating set since we are generating the whole space from this. Okay, so generating set you can treat as like a set of vectors, and span the space produced by those vectors. You know, to summarize completely, like let me write that generating set is basically the vectors, and span is space produced by those vectors. Now let's talk about bases now. So suppose we have a vector space V and we have A, which is a subset of V. So as you know that A is called the generating set. Okay, so A is the generating set if span of A equals to V. That is, you can get every vector in V by combining all the vectors or the vectors of A. Now there's something called minimal generating set. Minimal generating set. So a generating set A is called the minimal if there is no smaller subset A prime which is a subset of A that still generates V, right? In other words, like, you cannot remove any vector from A without losing the ability to generate the whole space. So like in this, every vector in A is essential if we want to get V. Okay, that is the minimal generating set. Like in a generally in generating set, if you suppose remove one or two vectors, then also if we can get V, that is called the generating set. But in a minimal generating set, every vector is equally important. Like you cannot remove any vector from that. And this, the concept of minimal generating set gives us the basis. So every minimal generating set is called the basis of V. So every minimal generating set is called basis of V. So basis is a set of vectors that is first linearly independent, because minimality ensures no vector is redundant, right? And second is it generates the whole vector space. So two conditions for something to be called as basis. First is they should be linearly independent, and second, it should generate the whole vector space. So now again, suppose if we have a set V which is a subset of our vector space and B is not a null set. So B is basis of V if B is minimal generating set. So the minimal generating set is, like, as I told you, that we cannot remove anything from that. Whereas maximal, it is also called as maximal linearly independent set of vectors, because if we add one more vector to it, the set will become linearly dependent. So every vector X, which is a subset of V, is a linear combination of vectors from B, and every linear combination is unique. So to put the things in expressions, right? K I equals to 1 till K. Simple. Now if I, to give you an example, if I have three-dimensional space, so three-dimensional standard basis. So standard basis is like the standards, right? Suppose 0, 1, 1, 0, right? For this is the standard basis for 2 dimensions. For 3 dimensions, these are the standard bases. 0, 1. So yeah. So like if I give you an example, then I have a set A which has, suppose 1, 2, 3, 2, negative 1, 0, 2, so I have 4 here, then 1, 1, 0, negative 4. So now the question is it a basis for R4? And like how to find whether is it the basis or not, right? So for that, what we can do is we just write all the vectors here, 1, 2, 3, 4, 2, negative 1, 0, 2, 1, 1, 0, negative 4. Okay. And then we convert it into the row echelon form. So it will be 1, 2, 1, 0, minus 5, minus 1, 0, 0, 0, 0. Right. So we have this, this, and this. So as we have 3 pivots in this, so from earlier lessons you can tell that C1, C2 and C3 are linearly independent. Now to check whether something forms the basis or not, there are 2 conditions. First, they should be linearly independent, and second, again, they should span the whole space V, in which our case is R4. But after getting the row echelon form, we can see we are only getting 3 vectors. So its rank, what I'll tell you like in some time, so its rank is 3. Hence, we can't traverse the whole 4-dimensional space in that. Hence, it's not a generating set, and it's not a basis of R4. So every vector in space V possesses a basis B. Also, there's one more thing, that there is no unique basis. So if I have, suppose, 1 0 and 0 1 as basis of our two-dimensional space, then we can also add lambda 1. We can also multiply with lambda 1 or lambda 2, right? So there is no unique basis for any space. So there can be many bases in the vector space, and all base possesses the same number of elements, which we call as the basis vectors. So all the vectors which is present in the basis space, we call them as the basis vectors. Now we only consider finite dimensional vector spaces V. So if I have to find what are the dimensions of V, it is equal to the number of basis vectors of V. Number of basis vectors of V, which is like the number of independent directions that we have in our vector spaces, right? So if we see in 2D, we have 2 independent directions. Hence, its dimension is 2. Okay, so dimension of a vector space is just basically the independent directions are there, or the number of basis vectors, right? Basis vectors represent the independent directions only. Now, just like our vector space has bases, subspaces also have its bases. So if we define U, which is a subset of V, so U is a subspace of V, then the dimension of U is less than or equal to the dimension of V, and dimension of U equals to dimension of V if and only if U equals to V. So basically, a basis of a subspace U, which is equals to the span, or which is means the basically the space, right? This represents the space, which is a subset of n-dimensional space, can be found by executing 3 steps. First step is write the spanning vectors as column of matrix A. So spanning vectors, so what all vectors is present in this, so these are called spanning vectors, so we'll write them as columns of matrix A. Second, determine the REF, so we'll find the REF of A. And third, spanning vectors associated with the pivot columns forms the basis of U. So spanning vectors associated with the pivot columns are basis of U. So if we do an example, now I have a vector subspace U, which is a subset of 5-dimensional space, and it's spanned by vectors x1, which is 1, 2, -1, -1, -1, x2, 2, -1, 1, 2, -2, x3, 3, -4, 3, 5, -3, x4, 1, 8, -5, -6, 1. And all these belong to 5-dimensional space. Now the question is, what is the basis of U? Basis of U. Okay, so which all vectors represent the basis of U? So for this, we'll follow the steps. So according to the first step, spanning vectors, these are vectors, and we'll write them as columns of a matrix A. So I have my matrix A, which I'll write as 1, 2, -1, -1, -1, 2, -1, 1, 2, -2, 3, -4, 3, 5, -3, and -1, 8, -5, -6, 1. Now, in second step, we'll form the row echelon form of our matrix A. So, after doing some transformations, this is what we get. 1, 2, 3, -1, 0, 1, 2, -2, 0, 0, 0, 1. So yeah, so we get this, and this is the row echelon form of our matrix A. Now, if we check for pivots, so this is the pivot here and here. So x1, x2, x3, and x4. So x1, x2, and x4 are linearly independent. So these forms the basis of U. Now again, like some of you will think that in the previous example, which is this, here also we had all the three columns independent, but then why it didn't form the basis of A? Because in this we were determining the basis of A, which was of a 4-dimensional space, right? But here we are determining the basis of U, which is a subset of a 5-dimensional space. So if I call about R3, right, then for my U, which is a 3-dimensional space, for that we have the bases x1, x2 and x4. But if we had U, which was R, which was a 5-dimensional space, then these vectors won't form the basis of that U. So next we'll come with we'll understand the concept of rank. So rank is just number of linearly independent columns of matrix A, which is of m cross n space. So rank is also, so this is equal to rank, which is also equal to number of linearly independent rows, and it can be represented as rank of A, so like that. Now the properties that we have are, first is rank of A will be always equal to rank of A transpose. Why? Because number of linearly independent rows equals to number of linearly independent columns for rank, and in row what happens in transpose, we interchange columns and rows, so it remains the same only. That's why. Second is that again, like I'll just write it down, that how we found the bases, right? So bases can be found using Gaussian elimination to A to identify the pivot elements, right? So we just do for bases, we do Gaussian elimination and identify the pivot points, pivot calls. Next is for all A, which is of n cross n space. It holds that A is irregular if and only if rank of A equals to n. So what it means is that if you remember irregular, so irregular matrices are non-invertible. So what this means is that if we have a matrix A which is of n cross n, that is, it's a square matrix, so it holds that A will be irregular if and only if the rank of A will be equal to n, which is a dimension. Next is that for all A, which is of m cross n space, the subspace of the solution for A x equals to 0. So the subspace of this x has the dimension n minus rank of A. So, and last is that rank of A is the minimum of m or n, which are the dimensions, for full rank. Else we call that the rank is deficient. Okay, so if the rank is either m or n, the minimum of them, it's called a full rank. Else we call it the rank is deficient. For example, suppose I have A equals to 1 0 1 0 1 1 and 0 0 0. So I check the pivots. This is the pivot. This is the pivot. Right. So in this, I have a rank of A equals to 2, and it was a 3 cross 3 matrix. Hence, it is rank deficient. Shit. So how is this connected to ML? So we have, say, machine learning, which constantly searches for low dimensional representations, right? Why? Because real data often contains redundancy, and that's where rank helps us to measure that. Now, linear independence taught us how to detect redundancy, basis removes redundancy, and rank measures how much unique information remains. And that's this entire video in one sentence. In the next video, we'll study about linear mappings. Until then,